Okay, so recording now, and we have Petar. Really should have asked your last name pronunciation, but I'm going to say Maymounkov
Awesome.
as a good guess. Great, and he's
Yeah.
going to talk to us about secure decentralized reputation system, SybilLimit. So go ahead, Petar.
Cool, thank you. So thanks everyone for listening. This is my first talk at PL. And let's see the key. Yeah, there we go. So the talk is mostly essentially describing the contents of this paper called SybilLimit, which I like and has good ideas in it. And I have interlaced, essentially, sort of overlaid on it some simplifications that I've made, which make the algorithms simpler but don't lose security guarantees. And I've made some small improvements in the security guarantees as well. Okay, so first, I want to give you some context of why we are talking about this. What's the motivation? So PL and outside of PL, people are building already quite a lot of different decentralized applications, which solve for different sort of problem areas. Our notable examples are Gossip Sub, which is a system for broadcasting messages, and the DHT, which is a system for key value storage. And as the number of these kinds of decentralized applications grows, it becomes very difficult to make sure that every single one of them is robust in a formal sense that we care about. So the point of this line of research and reading papers and thinking is to come up with a one-off general way to make at least most decentralized applications robust right off the bat, as opposed to trying to take care of robustness for every single application with all the complexities and specificities that it might have. So for instance, broadcast and Gossip Sub is a very different system than the DHT. And so if one is to try to make them Sybil resilient and so forth in an ad hoc manner, it ends up being error prone and it takes too much time. So briefly, when I talk about robust decentralized systems, I mean it in a formal way, but for now it's just, I'll just mention it informally. So at least we have to have 4 properties. Open membership is clear, and it's basically the philosophy of why systems are decentralized. Surviving, I'll go in detail in a second, but surviving is just the notion that it has to be able to continue living through some reasonable conditions over time. Scalable is clear, but just to give an example, a broadcast system where everybody talks to everybody else, like a V1 Bitcoin ledger, is not scalable because of the dense connectivity. And finally, as a standard, distributed systems should be live, which just means responsive, even in the presence of failure of individual components. So I want to be able to achieve these 4 things more or less generically, regardless of what decentralized system I am designing. Now, the hardest part at the moment that I want to focus on is what does it mean for a system to be surviving? And essentially, this kind of means a few things. First of all, it should be able to tolerate malfunction, of a sort of fair malfunction of its participants or the network. So this essentially means non-Byzantine failures. It also should be resilient to malicious behavior, which I guess in the decentralized literature is generally referred to Sybil attacks. And here, I want to essentially make a distinction between 2 kinds of Sybil interferences, which don't have a formal distinction, I guess, terminology in the literature, but I'll call them Sybil attacks versus Sybil infections. So Sybil attacks, most of the literature and practice tends to refer to the term Sybil attacks as essentially taking care of mitigating an expressed malicious behavior. So once the malicious parties have actually started deviating from a protocol, this is when people tend to refer as a Sybil attack. And so mechanisms for mitigating those tend to be mechanisms that first sense the deviation from behavior and then respond to it in some adequate manner. What's much less covered in the literature, and I imagine in practice, is this other vector of attack, which is, for a lack of a better name, I call it Sybil infections. And the idea of this is really the case. How do you deal with adversaries entering your decentralized system and behaving correctly for an extended period of time in order to gain basically presence in some significant fraction of your system? So defending against those is a little tricky, it seems, just due to lack of much results. And so this is what I'd like to focus on. And I'd like to be able to solve this problem for at least for GossipSub and Kademlia, so that we can sleep well at night, basically. So this is the line of work that sort of started with, let's read the SybilLimit paper and see where we get from there. Okay. So I want to give you some expectations, essentially, of what you'll learn. So I found that this paper has very good and strong technical ideas in it, which are worth knowing about, and you could use them as building blocks, essentially, of other systems you're working on. The holistic solution that the paper itself offers for handling Sybil infections is, it's an open question whether we could use it somewhere usefully. I find that it's difficult to find an application for it since its user interface, so to speak, is counterintuitive, and it does face the actual users. And also because the strength of protection is not quite sufficient for some decentralized applications like Consensus, which cannot handle more than 25% of misbehaving nodes, basically. So it might not be perfect for GossipSub. But the big upshot from spending time with this paper was that I was able to essentially reuse and extend the low-level techniques in this paper to come up with a solution that is robust and works for broadcast, so for GossipSub. And I hope to be able to present this sometime soon, basically. Okay. So technically speaking, SybilLimit talks about secure decentralized reputation system. And let's dive into this and understand what this means. A reputation system, so for a start, is a system that, motivationally speaking, is trying to help you identify communities inside graphs. And the notion of community is up to modeling. So there will be some modeling choices involved in any reputation system. So a little bit more formally speaking, it's a system that essentially is a graph database. It allows you to add and remove edges and vertices. And it essentially gives you only one type of query that you can ask at the graph, which is, are two vertices well connected? Does this make sense so far? Everything's good? Okay. So this notion of connectedness has to somehow reflect what we intuitively mean by social connectedness. So are we in the same sort of circle of friends, or are we very far away from each other? And this notion has been formalized for a few decades now in mathematics, basically, by a very clean definition, which tends to fit also social measurements and observations of communities. And the definition basically of the connectedness between two vertices is essentially aspiring to compare the size of the bottleneck between them in a graph compared to the size of bottlenecks of vertices that are much closer. So it's a technical definition and usually takes a while to absorb. So I'm putting it out here just so you have it in front of your eyes. But it basically, if you look at, I have two communities in this picture. If I want to ask the question, how connected are X and Y, intuitively, I want the answer to basically reflect the bottleneck between them, and versus X and Z, which are in a much more densely connected component. There is also a bottleneck between them, but it happens to be as large as the component itself. And so this is captured in this definition, which just says that the connectedness is the number of edges that cross the smallest cut between the two vertices that you care about, and all of the edges that are on one side of the first vertex, basically. This is a asymmetric definition.
Is there a way to make it symmetric?
There is. So the way to make it symmetric is actually quite simple. You take the minimum of the edges on the side of X and the edges on the side of Y. And in fact, the symmetric definition is what you will see in all papers, because papers usually care about just finding a bottleneck in the graph. But when you are talking about reputation, we're going to be asking questions from the point of one vertex, is the other one part of my component? And so that's why the asymmetric definition is going to matter in our case. Cool. Another way to intuitively think about this definition, it's actually provably sort of equivalent, is this is also measuring the number of these joint paths between the two vertices, because you can intuitively tell that the number of these joint paths would be essentially determined by the bottleneck. Okay, and I have a couple of examples here. I mean, just to get your mind going. So the connectedness between X and Y is, there's two edges on the cut, on the smallest cut between them, and then there's 10 edges on the other side. So it's much smaller than the connectedness between X and Z. Okay, so this is kind of like the gold standard of what reputation systems are trying to accomplish, to be able to compute these numbers. But this is an NP-hard problem, so it's not practical to shoot for this. So instead, systems and actually mathematicians in general take a different approach, which uses what's called a dual formulation of the same question, which is almost equivalent to the original question, and produces results that are approximately the same number. So the dual thing of trying to find bottlenecks is to actually look at the behavior of diffusion processes. And so a diffusion is simply just a nomenclature for the distribution of the last vertex of a random walk. So if I take a random walk from a point, I look at the cloud of where it can reach, and I'll just be calling this thing a diffusion. And so there's a sort of famous duality, very well known, very commonly used theorems that say that two vertices are well connected in the original sense that we talked about if diffusions from both vertices overlap a lot. And they're not well connected if they don't overlap a lot. And I want to give you some intuition here. So if you have a vertex in some well-connected component, a diffusion would still mostly inside the component because random walks are going to tend to stay inside it. But there'll be small pieces that kind of go towards the bottleneck and maybe even cross it. And the whole point here of this duality theorem is that if you have two vertices that are in the same component, their intersection is going to be large compared to two vertices that are coming from different components, in which case the intersection would be smaller. And so reputation systems are really systems that measure connectedness using this, this notion. And just to connect it to something real that you might be familiar with, so PageRank is very much a reputation system of this type, in the sense that PageRank is a random walk, which is defined as take a random, at each step, take a random edge, or terminate with some fixed probability. So it's a random walk where the length of the walk depends on a variable, and otherwise it just takes random edges. And so PageRank fits in this definition as well.
For this diffusion, there is an expected length of these random walks, right?
Yeah. So the length of the random walk. So we choose the length of the random walk, and I'll show this later, based on how large the cluster that we think we're in is. But there is a simple trick that makes it so that you don't actually have to know the size of your cluster. You can simply, in parallel, use a few powers of two different length walks and just compute the answers for all of them at the same time. But yes, the length of the walk depends on the size of the cluster that you think you're in. Yeah. Okay, so that's what reputation systems are. They compute connectedness between two vertices. Now, so what's a decentralized reputation system? So the difference here would be that the vertices are not abstract data points, but instead they are the participating compute nodes themselves. And the second difference is that participants can only add and remove edges that are incident to themselves, basically. Otherwise, the query type of the question that we can ask remains the same. So that's a decentralized reputation system. And the final step is to see what is a secure decentralized reputation system. So in this setting, we again have nodes as participants, but we also believe that an unlimited amount of nodes can be malicious because it is valid behavior for anyone to be joining the network by creating edges to other nodes. So we are expecting malicious participants, and the notion, so we assume essentially that Sybil behavior represents essentially convincing a few good, honest participants to create edges to ourselves, and then be able to create a multitude of bad edges sort of in the Sybil. Once we have a connection into the honest region, then create more and more and more to create a number of Sybils that's larger than the honest nodes. And the problem that secure decentralized reputation systems are trying to solve is to be able to ask the question, if I'm an honest node and I want to check if another node is Sybil, really I want to check whether I'm separated to them, separated from them with a small bottleneck. So the presumption is that a Sybil party would not be able to have a large number of edges to an honest community. And therefore, we want to be able to check for this, which is exactly what a reputation query is for. And in the case,
quick question: what does it mean to have an edge as a participant in this community? Does that mean that you like have a relationship? You've like shared some computation interact? Like, what does that look like to add or remove that?
Yeah. So excellent question. I didn't give enough detail. So in a decentralized system, just computationally, the system says vertices can add incident edges. And I kind of left it at that. The intended application of this is that nodes, so the best example of this is like social connections, but what an edge means is up to the application layer, but really this is motivated by the case where pairs of people can individually decide that they're friends, and so they can create an edge between themselves. So creating an edge is essentially, in the motivation of this paper, corresponds to human-to-human contacts where two parties decide that they trust each other, and so they're going to formalize this by creating an edge into the system. So, but more generally, what an edge means is open for how you're going to use this system. If you're a user, if you're an application using the system, you have to decide how you want to model an edge, and making it so that users enter their social contacts as an edge is like one of the obvious things to do. There are other options that I'll mention, but the system itself is essentially offering you one thing. It says that it can tell you if somebody is in the same cluster with you, as long as the two clusters are separated with a bottleneck. And so you as the user of the system have to figure out how should I be creating edges in my system so that this is a useful primitive for me. So it's kind of like, you understand. So, but in simple words, it's really just, you can think of edges as being actual social relationships. And this is a viable scheme under the belief that that a malicious party trying to enter into a real social community would have a hard time kind of cheating too many people into creating friendships with them. The classical example, if you have like a music sort of sharing community, it's very unlikely that too many users are going to be tricked into having friends that work for,
But this is exactly the crux, right? Is there's some expectation of a barrier, where it is harder for the adversary to generate these edges versus real people, and you have to figure out how that actually works in practice.
Exactly. So this is the contentious part about, is this applicable or not? Because the guarantees of this algorithm are going to be that if the bottleneck between good and bad guys is less than 5%, then I guarantee you that I can tell the good guys from the bad guys. But if it's more than 5%, all bets are off. So that's why I mentioned earlier, this interface of creating a social system is counterintuitive, and it's not very clear whether in practice, what's the right number? Do you believe an adversary can take 5% or 10%? It's hard to know. And the last thing to say about the secure case of these systems is that because now we are going to be tolerating intentionally malicious behavior, you get a yes/no answer as opposed to a graded measure of how close they are to you. You get a yes/no answer, which is yes, they are an honest guy, as long as the bottleneck is bigger than 5%, and no, they are a dishonest guy if the bottleneck is less than 5%. And this answer itself can have a small amount of false positives and false negatives that we'll quantify later. All right. Do things make sense up to this point? Okay. Yeah, and so what I just mentioned is that you should expect to have false positives and false negatives, and they are to the order of the amount of sort of misclassifications is going to be roughly sort of equal to the size of the bottleneck, because that's where confusion arises essentially. Okay, so these are some results from the original paper, which are not to be taken too seriously because, first of all, they are from a very specific network, so they're from Friendster. And secondly, because they don't incorporate the small improvements that I've added to the protocol, but I think in spirit, things are somewhat accurate here. And what these graphs are saying is that essentially when you have about 5 to 7% of attack edges, so they use the term attack edge to mean any edge that, between a Sybil and an honest person. So by the time you get to 5 to 7% of attack edges, then the number of sort of the number of misclassified Sybils that you accept is as large as 80%, which is the same thing as saying is that you are working with a network of people where 80% of them are actually bad. And this is too weak of a guarantee for an application which is consensus, which requires only 25% to be bad. But again, you know, take them with a grain of salt because these are very old numbers. Okay. So the question about applications of this paper, I kind of see that they fit in two categories. The first category is subjective sort of meanings of an edge. The most obvious one is using the actual user's trust relationships in real life to mean an edge. So having a system that asks users to link up friends. So it is subjective. There's a couple of problems with it. Sometimes a product doesn't, being social doesn't sometimes make sense. Like for instance, this would create a lot of friction if you asked DHT and GossipSub users to be creating social networks, so that's one caveat. There's a second caveat here, which is a little deeper, which is that even if you let users create sort of trust edges, any one user doesn't have a global view of the graph. So the feedback loop is kind of very bad because the user doesn't really know what they're supposed to do in order to improve the health of their community. So it's kind of a it doesn't seem to fit very nicely. So these are caveats with the obvious use of edges. There are other ideas that I've thrown here. You can use an edge to mean a monetary transaction between people. So in a sense, you get sort of a system that looks like a club with membership fees, but I don't know what applications of this would be. It suffers from the same problem that an individual user doesn't know when to accept a new member and when not to, because they don't have a view of the whole system themselves. And there's another class of applications which I find more interesting potentially. And these are sort of objective ones where the graph that you create is linked to something that's about your system itself. So one possibility is to use lineage relationships. So you could keep track of the kind of like the tree of parents. Like if I join the network through two people, you could view them as my parents, and then you can build a graph of these lineage relationships. And is this useful, right? And the final idea was to have an internal notion in the application to mean an edge. So in Gossip Sub, for instance, two nodes could have an edge between each other, a reputation edge, if they have scored each other well, which means that they approve the amount of work that was done by the other node. So that's I think that's a fruitful direction. And I actually tried to see if using this paper and using the definition of an edge to be somebody who scores high in the Gossip Sub sense, whether this allows for a good protection against Sybil infections. And it turns out that it doesn't because of the weak guarantees of the protocol itself. But I was able to take this idea in a slightly different direction to produce this future work that I might present soon. Otherwise, it's open for you to also think of ideas. Okay, so I should stop here and ask for questions. Yeah.
Yeah, I'm just curious why you labeled the last of those four objective. It seems like a subjective evaluation between two nodes.
Oh yeah, sorry. So objective ones, the ones that are labeled objective, are ones that come from algorithmic measurements from your system. So who joined who is something that's a recordable piece of data. Like when you joined, Gossip Sub for the first time, you could write down what was the node IDs who joined you. And for the introspective one, I mean, it's an objectively measured quantity. What is the score of another node? It's produced by objective. I mean, it's produced by the algorithm. It's not produced by a human, basically. Maybe it's bad, bad wording.
That makes sense. Thank you.
Mm-hmm. Okay. Any other thoughts, questions?
I have a question, but perhaps like it's not really a question. It's just like it seems to me that the application this algorithm is highly dependent on having a way to kind of like declare which nodes are part of the network and which nodes are not part of the network. Like it really like it ends up being like a question of like, can we really judge a node before creating an edge with that node? Do we have a really good model to say that that node is part of the group or outside of the group before? Yeah.
No. So this. So again, it depends how you use it. If you use edges to mean social contacts, that also defines everybody is part of the network, even if you don't have any edges to anybody.
Mm-hmm.
But when you end up having an edge in the social graph, when you end up having an edge to anybody in the network, you automatically become part of the network. The only difference is that you probably become part of the network. Can you see my mouse cursor?
Yeah, we can.
So if you just created this friendship here, you are part of the network, it's just that you will have to create more friendships before you are considered part of the honest region. So entering the network in some sense means getting somebody to create an edge for you.
Mm-hmm.
But that doesn't enter you with high reputation. You actually have to have many edges before you start being considered an honest person. And Sybils here doesn't actually mean necessarily actual malicious nodes. Anybody who joins far away from the core of honest nodes would be viewed as Sybil until they have enough edges to not have a bottleneck to the honest nodes. So joining is simply just the act of a friend of yours who already uses Gossip Sub accepting an edge from you. And in this model, you would have to find a few people who run Gossip Sub, have them to accept you, and then you will become a sort of equal member.
Interesting.
Another way maybe putting that is that this is connectedness in the trust graph, which can be different from network connectedness. So you may allow an untrusted node to make a network connection. So you can have like different levels of either like how you will use this sort of overlay trust graph for as a higher barrier.
Understand, and it makes sense. I'm just like trying to understand like if how this compares to the existing solution that we have, especially Gossip Sub that has like a scoring system, right? Because the way that I see this,
so the big difference. So here, the big difference, right, is that Gossip Sub does create. Gossip Sub implicitly has edges, in the sense that I can postulate that Gossip Sub has an edge between two vertices if there is a high score on this vertex, right? So basically the vertex, but so you end up having a graph, but Gossip Sub doesn't have a notion of computing remote, so connectedness between remote vertices. So Gossip Sub only uses the scoring to judge its immediate contacts, so the incident vertices. Whereas this system is saying,
so there is a reason for this, though. There is a reason for this, is that in general you don't know the activity of the other peers.
Yeah.
And it's also explicitly has been asked from Filecoin to make it as hard as possible to deduce the topology of the network, because this can open avenues for other attacks. So we literally cannot do this.
Yeah. So I'm not saying that's a criticism. I'm saying this is a difference. So because the key thing about this reputation stuff is that it's giving the power of nodes to create edges locally, but then it's giving them the service of knowing something about the global result. So the local global relationship is the sort of the key part here, and it's not necessarily applicable as is to Gossip Sub.
Gotcha. So I think I managed to kind of like formulate exactly the question I have, and I think that what I don't understand is if this model works for high churn networks. It seems like it really relies on a stable network of like well-trusted peers that have created an edge for some reason, reputation, social graph, etc. But like in an event of nodes coming and going really fast, that this model would be less efficient at giving us the right answers.
Sure. It depends though, what is an edge again, because if an edge is manually created by users, definitely doesn't work for high churn situations, because users can't react quickly enough to a change of opinion about trust. If an edge means something that's computed from your system internally, then it's a different situation. It means that this graph can change very quickly with sort of changing conditions. But again, I actually, it's worth kind of going, maybe not now, but going through your head with an example of what would happen if these edges mean a high score in Gossip Sub.
Yeah, exactly. Yeah, so that's what I wanted to mention before, that how you start building the graph that Petar has been talking about depends on what input you give to the system. So one possible input could be the score that we have in Gossip Sub. So it's not, I mean, I don't know if it would work, perfectly, but
the score changes in seconds. The score changes within seconds.
So ignore time. The question is, what does it mean? So that's the harder question. So ignore how quickly it changes, and sort of, I think the bigger question here is, if these edges mean work, is it natural for us to say that two disconnected clusters are in fact an honest one and a bad one? And so to be honest, the answer is yes, because I've thought about it, and so here's why, right? So this certainly models one type of Sybil attack where you have a bunch of guys, the honest regions, that are doing lots of work for each other. So this is like Gossip Sub working in sort of perfect intended regime. And then you get a couple of new guys that do work. So these are the red edges. So a couple of guys connect to the honest guys, and they do good work so that they're viewed as good. But then they start connecting lots of copies of Sybils behind them, and because they're all Sybils, they score each other high, even though they are not doing any work. So this is a perfectly valid scenario, this algorithm would basically tell you the right thing. It's just going to, it's not gonna, an honest node won't accept somebody behind the bottleneck, precisely because you get the right thing, right? So you get this replication of false scores not to affect the decisions of the honest nodes, basically. So I think I can compare, and hopefully I don't make a mistake, but the challenge in Gossip Sub when you want to change who your mesh is that in some sense, you have to sample from the set of all possible peers, which essentially means that you have to sample uniformly from both the theoretically Sybil and honest nodes. And so if you have like a 99% of Sybils, the chances of sampling a Sybil are very high. But if you had a reputation system, then you would be sampling uniformly from the honest nodes, and you're not going to be sampling anybody from the Sybil region, which means that you might avoid the need to resort to flood sub, for instance. And so actually, I do think that this would work, but the reason why the thing as a whole I don't think works is because the misclassification percentage of this algorithm is a little too weak. Conceptually, I think it does apply.
I guess I have maybe another way to think about this is probably the useful graph theory framework that you want to fall back on to get useful theoretical guarantees out of any of these sorts of overlay networks, right? Like if you're going to try and say that you have Sybil protection, this is sort of I think the space where there is some way to have a claim about what you're doing. You need to have some sense of what it, of an ability to segment a network and actually look at it from a graph theoretic thing. And that all of this sort of Sybil space is looking at some sense of a scarce resource where it is easier for your trusted cluster or clique to have that than Sybils. And in this case, we're looking at trusted links or friends or social or these various things as that resource that is difficult for a Sybil to acquire. Whereas, you might use IP addresses or network resources or computational resources. This is, I think a lot more believable in a lot of ways than those, right? Because if I say it's computational resources, an adversary can actually spin up a lot more computers than an honest node, and so that has its own problems. So
I'm wondering whether we should put this discussion at the end, just because we're running to the hour, and I wanted to give you a sense of how it works on the inside. And in general, it is a worth discussion, but I think even when edges mean work, it's possible to get sort of meaningful outcomes from this. But let's put this at the end so we can finish like all the sort of fun bits, basically. Cool. All right. So now I'm essentially going to show you how the system, what's the protocol and what's the proof that it works. And so for this proof part of for the formal part of the talk, essentially, I want to spell out what are the assumptions. So the assumptions is that we have a graph which has one component which we call honest, and everything else is separated from it with a sparse cut, which formally speaking is a cut of, think of it as 3 to 5%. And everything on the honest side is doesn't have sparse cuts. So it's high conductance is the term for this. Okay, so this is the assumption that the graph looks like this. Really, this is saying CBUs don't have more than 5% attack edges, basically. They can have less, of course, or they could be non-existent, but no more than 5. So that's the assumption of the paper. Otherwise, nothing works. The plan for the proof is going to be roughly like I mentioned earlier. Essentially, we would get an algorithmic way of having the diffusion from an honest node, which is trying to verify whether another node is honest or not. So we're going to get this diffusion as a data structure that has a square root of n numbers, so small size. Essentially, every node would basically have a signature, which is the diffusion away from it. And we're going to make a judgment based on whether their signature, the intersections of these diffusions are big or small. So now we just have to fill in the details. First, formally what the algorithm does. For every vertex, the algorithm says that the vertex should go out and collect square root of n random walks away from itself, and they should be of length log n. And this is the signature of the vertex, so to speak. In other words, we are representing the diffusion by sampling square root of n random walks from it. And so I'm calling the vertex V here in this picture. And in fact, the only thing that's interesting is what is the last edge of every walk. So the diffusion really is this collection of edges that you can reach. So T1 to T2 and so forth to T5, they call them tails in the paper. Every vertex generates a signature like this. And when two vertices want to, when we have verification, we have a verifier vertex and a suspect vertex. And so the verifier is checking whether the suspect is behind the bottleneck or in the same component. And the verification algorithm has two conditions. It says that to say that the suspect is an honest node, first, I want to verify that their diffusions intersect. That's the first condition. And the second condition is a little trickier to say, but it's the following. So every verifier keeps a count of how many suspects it has accepted as honest through each of its tails. So the tails are the tentacles at the end of the random walks. So I hope this picture makes sense. So basically every time you accept a suspect, you increase a counter and you have freedom which counter to increase. So if you have multiple common edges with the suspect, you can increase the counter on any one of them. But when you are increasing the counter, you have to make it so that the imbalance between the lowest count and the highest count doesn't grow by too much. In other words, you have to keep the vector of counters balanced. And so in this example here, the verifier and the suspect intersected tails 2 T2 and T3. So the verifier could either increase the T2 counter or the T3 counter, but increasing T2 would make the vector 2 imbalanced, so they would increase the T3 counter. So as long as you can increase the counter without violating the balance condition, then you can deem the suspect as being an honest node. And now, just to mention for your intuition, remember we said that honest nodes are going to have much bigger intersection on their diffusion processes, which means that they'll have many more choices of which counter to increase, which later will prove guarantees that they will always find a spot where to increase a counter. And this won't be the case for Sybil nodes, as we'll see. Okay, so this is the verification algorithm. And before we move to the proof, I have to tell you how is it that when a verifier and a suspect communicate to each other their signatures, in other words, the random walks that they performed, how is it that they cannot lie about this? So this is this neat little trick that I guess they call verifiable paths. The idea is that, so the question is, we need to specify how does a node generate one random path away from itself. So the path, first of all, has to be pseudo-random, so they cannot lie about it. And it's defined in the following way. So the first edge of the path is somehow a hash function of the number of the path, because remember, you have to have square root of n paths. So it's a hash of which path you're currently traversing, and also your own node ID. So that's good and all right. The more interesting rule is that every following edge is only a function of the previous edge and the path number as well. So this is the key part which ensures that Sybils cannot generate an arbitrary number of paths into the honest region, because the fact that an edge depends only on the previous edge implies that no matter how Sybils can manipulate the paths in the Sybil region, once they cross over into an honest node, everything else is determined from there. So that basically implies that the number of fake paths crossing through the bottleneck is proportional to the size of the bottleneck, basically. So that's a very cool trick. And the actual path collection, how does a node essentially collect all these paths and present them to verifiers when it needs? That's trivial. You basically do a random walk and have all the nodes sign the steps, basically. So that's nothing special. Okay. And with this, we are ready to actually prove that this works. And so what is it that we're trying to prove? So the statement formally is that most honest verifiers, in other words, most honest nodes, will accept most honest suspects. So in other words, we won't be able to accept all of them. We're going to have a false negative on some suspects, but we want to do okay on most of them. And we're going to accept very few of the Sybil suspects. So people who are Sybils and are applying for verification, few of them would be accepted. And to put some numbers on this, so most honest verifiers, that simply means all of them except for a fraction, which is equal to the infection. This is the 5% number, or attack edges divided by honest edges. But using basically the same epsilon that is the infection of the edges tells you how many of the honest nodes are actually going to be functioning properly as verifiers. And then they will be able to correctly identify 1 minus epsilon of all the honest guys, and they're going to let in an epsilon fraction of Sybil guys. So that's the guarantees, and we're going to prove this in 3 steps. Actually, does that make sense?
I would like a quick clarification on the 5% of Sybil edges that you mentioned.
Mm-hmm.
Maybe now that it's not the right time to clarify that, but can you repeat what is the 5% assumption?
Yeah, so in general, the assumption is that the attack edges divided by honest edges is a number that is small. So 5% is an example. So the actual assumption in the paper is they have to be less than square root of n. But the thing is, I wouldn't go by asymptotics because they're not very enlightening when it comes to real world graphs. Basically, they don't, like, even the results in this paper actually seem to be working for much higher than the analysis predicts. And so I think the analysis itself works for edges fewer than square root of n, basically bad edges. And after this, it probably still works, but the analysis doesn't capture this regime. So for networks of reasonable size, this analysis is kind of targeting the 3 to 5% range of maximum acceptable infections of edges, basically. And so 5% meaning infected edges divided by honest edges. So.
Okay, let's carry on. Yeah, thanks for the clarification.
Okay. First step, so right off the bat, there is this follows directly from the definitions that the honest region has high conductance, so no smoke cuts. It directly follows that for 1 minus epsilon fraction of the honest nodes, any random walk from an honest node in this fraction is going to land completely uniformly on an honest edge. So a random walk from most honest nodes lands on a uniformly random edge in the honest region. So this is like our first step. And in fact, we're only going to focus on proving the guarantees of the theorem for these honest nodes for which this property holds. You know, and this should be intuitive because you can't guarantee this for all honest nodes, because the honest nodes that are close to the bottleneck have an obvious chance of escaping into the other region, which is much higher. Okay, so starting from this assumption, we just need to prove two things. The first thing is that an honest verifier will accept an honest suspect. And the second thing is to prove that an honest verifier will reject a Sybil suspect. So first, why would we accept an honest suspect? So as we said, each vertex has square root of n tails, random edges, that they generate as part of their signature. And if two nodes are honest, their tails are going, all of their tails are going to be randomly and uniformly distributed in the honest region. So in other words, whether they intersect is really the question of, if I throw 2 square root of n balls into n bins, are they going to meet? So it's pretty simple. It's the birthday paradox, and so the answer is yes, if you just kind of do the math. So, and more generally, basically, the simple fact to remember is that anytime you're throwing more than square root of n things in n buckets, you always pretty much are going to get like at least 2 somewhere. In other words, there is an overlap. So this is the proof that 2 honest suspects will have an intersection in their tails. And we have to also take care of the second condition, which is that they will be able to increase a counter without violating the balance condition. And this follows from the fact that honest nodes are actually not just going to have a single vertex of intersection, but when you pick the constant in front of square root of n correctly, you can guarantee that they actually have at least a couple, like 3 or more intersection points. And then there's another theorem which is called the power of 2 choices. Tells you that when you have an imbalanced vector and you're trying to increase one thing, but you have 2 random places where you could increase it, then you can do it and the vector grows sort of in a balanced way. Yeah, so this is essentially the proof that honest nodes will accept each other, and that because of the large intersection, the verifier is always going to be able to find at least one of the intersecting tails to be appropriate to increment a counter without violating the balance condition. Make sense so far a bit?
I think it makes a lot of sense. I just have like a lot of, well, I think what I will have to do is review the talk and then like make a bunch of sketches to organize the thoughts in my head and then ask you more questions. Right now, most of my questions are in the practicality of this in a live network, like IPFS1 or like anything with peer-to-peer. And the other thing is like, I don't necessarily, well, maybe the practical question for this session here right now is I don't necessarily understand the usefulness of knowing the path, because in the end, what they are looking for is the vertex that they both share. And so a Sybil node could just like happen to have the connected to the vertexes that are on the edge of the graph, and therefore match the same vertexes with the honest node, and therefore the honest node will trust the Sybil node.
Well,
right?
The algorithm is looking for intersection of the tails, the edges, not the vertices.
Oh, gotcha. So that needs to be at least a subset of a path, yeah.
And that's actually pretty key, because the distribution of random walks over the edges of any graph is uniform. It's not uniform over the vertices. Every vertex receives a random walk much more frequently depending on its degree, but every edge receives it with the equal probability. So that's why edges have to intersect. And I'm going to leave room for the practical questions just at the end. We actually have like just a couple more slides and we're done, so we can talk practical. So the last thing left here is to just prove that an honest verifier would reject a Sybil suspect. And so the question is, how can this happen? If you recall, an honest verifier has their diffusion process, their signature, which will mostly be in the honest region, and there will be a small piece into the Sybil region. And the chances for a Sybil to basically intersect with the honest verifier is what we're trying to limit. And there's two, the intersection between a Sybil's reach and the honest verifier's diffusion reach essentially has two pieces that we want to take care of. So the first piece is the tails of the verifier that might escape into the dishonest region, and their expected value is basically simply the total number of tails that the verifier produces, which is square root of n, times the probability that a random walk from the verifier actually escapes into the Sybil region. And I'll put in the numbers in a second. And the other way in which a verifier can be confused is if the Sybil so the Sybil nodes manages to create a tail into the honest region, and it intersects with the verifier. So the expected number of such edges where this intersection can happen can be decomposed as the total number of honest tails reachable by the Sybils. So this is the key term is there is a limit to how many edges in the honest region the Sybil can even reach in the first place, and this limit comes simply from the fact that there's for every attack edge, the verifiable paths can really only infect one tail because of this hash function that limits where they go after they cross into the honest region. So that's why we want to start with the total number of honest edges that can be reached by a Sybil, then apply to this the probability that the verifier even picks them at all, and then we have to multiply this by the number of times the verifier picks tails, which is square root of n. And so if you do the math, you end up having that the green region is really not a problem. It barely even constitutes one edge in expectation. But in the honest region, the verifier can infect about up to attack many edges sort of that are inside the honest region. This math actually shows that it's about attack edges times log n. This is the case if you use a random walk as in the paper with a fixed length, but I figured that if you actually use a PageRank random walk, you can shave off the log factor. Okay, so now we have a bound to how many edges can be intersecting between an honest and a Sybil. And so off the bat, this means that verifiers will very well be accepting Sybil nodes every once in a while, but in order to limit how many they'll be accepting, that's where the balance condition basically comes into play. So the balance condition says that, you know, if a verifier looks at all of the nodes that it had ever accepted, you want them to be balanced, to look like this. And we just proved that, so remember the x-axis corresponds to the tails of the verifier. And we just proved that only attack many tails can actually be tails where the Sybil can intersect the verifier. So even though the verifier doesn't actually know which ones these bad tails are, just by insisting that they maintain balance of all accepted nodes, they guarantee that the amount of accepted Sybil nodes is always going to be in proportion attack edges divided by square root of n to the honest accepted nodes, basically. And this is the end of the proof. Cool.
It's really cool, Petar. Really cool.
Thanks. So we can talk about practical stuff and questions, and I can open the chat window.
Awesome. Yeah, I don't know. I mean, yeah, so I guess one thing I'll add as context is I was working at UW with Ray, who was also under Kashuk. So I heard a bunch of these ideas when looking at sort of BitTorrent applied social overlays and was looking at SybilLimit a lot. So like in terms of how well you can do, this is, I think, absolutely the framework. And then the trick is, how does this bridge into practical systems?
Yeah. So that's so maybe I can tell you essentially what happened. So I'm actually quite excited because I did find a slam dunk solution for Gossip Sub, starting from this paper, but going in a very different direction. So my starting point was something that we talked about earlier. I said, well, what if these the edges are some internal notion of work. So maybe an edge means that somebody has been doing good work in Gossip Sub. But then the first problem that I ran into is that if you speak in this generality in which these reputation calculations work, if you just require that there's a small bottleneck between the bad guys and the good guys, the results that you get are very weak. Like I said, the probability of false positives, in other words, how many of these like Sybils they can kind of make honest nodes accept them, is like more than 50%, and that's just too much. And then I realized that you don't actually have to assume a social network coming from outside. Instead, I carefully crafted an algorithm for the honest guys. So it's like a slight modification of Gossip Sub. I basically carefully crafted an algorithm which results in honest people being connected, not just in some arbitrary high conductance component, but instead in a high conductance graph that I know exactly what it looks like and so forth. And then from this point on, knowing exactly the structure of this high conductance graph, I'm then able to essentially boost these guarantees significantly and so on and so forth. The point being is that the graph of honest nodes, when you have the power to create it, doesn't have to be just any graph. It can be something that's really working so that the analysis comes out, works out. And so this is what, so I've proven it, I've simulated it, and I'm working on kind of documenting it and being able to present it basically. And I am
yeah, absolutely. I think that a lot of the tension is the thing that you are doing in all of this sort of thing by making whatever these links of trust are your scarce resource to defend against Sybils is a form of gatekeeping in some way, right? You're making it difficult for people to join that graph. And so you have to balance that with your practical system of wanting to be open membership still, or wanting new people to join. And so it's how in practice is a node bootstrapping in a way that you're still allowing existing nodes to decide are they good or not? Because there's that tension of like, if that becomes too hard, people will like make other systems where they like get around it. So because people want invites, people want whatever, right? Like that practical thing really hits up against then is this really a working link?
So exactly. And so actually I don't like the intended application of this algorithm, which is that in order to join the network, you have to have some pre-existing social contacts, because this actually reinforces the richer gets rich sort of societal problems, mechanism problems. And so actually what I also wanted is to have sort of egalitarian open membership, which means that everybody can enter without context, but they will go essentially through an initiation process, which is entirely based on internal notion of work. So, you know, whatever that is. And so, precisely that's like where I'm headed with this.
So in practical terms, would that mean that you know, the system would prevent Sybils from entering a network that has already formed, and that, you know, there is a warm up assumption that, you know, initially we assume that everyone is an honest node, and then random guys start coming in, some of which are Sybils, some of which or all of which,
So the way this shakes out stated in a formal way, I think is slightly more general. So it just says this. So the result basically that I have, and any result actually could be only of the following form. It could say that regardless of what stage a network is in, it could be small, it could be large, but the statement is this: it costs like a malicious, it costs any party actually, because the whole point we're talking about the cases when we cannot distinguish malicious from not malicious, because we're looking at the case when malicious parties are behaving well. So that's why the statement is for anybody, Sybil or not, it takes a quadratic amount of work to become an equal member of the network. So equal member of size, K, however much size you're aiming to be, it takes a quadratic amount of work to get to size K, quadratic in the amount of work that honest nodes of size K do. So this is the result that I have. So it has to be a relative result, because that's the definitional requirement. But this is what I got basically. It just says that if you want to get a fraction, if you want to get as big as 10%, if you want to infect the network by 10%, you need to invest whatever 10% of the honest guys are doing squared. So I think that's like that's the part that like convinces me the most that it's like a reasonable guarantee. And also in the case of this newer algorithm that I'm referring to, there is no limit so the network can function properly up to any size infection, so 70%, 80%. You get to pick it as a system designer, and of course it blows up your connection count parameters a little bit. But for 70%, the connection count is reasonable, like 80 connections or something like this. So,
very interesting. Okay.
So if I may make a comment, I mean, the math is good, but I'm not convinced this can be practically implemented within a real-time system. So how are we going to do the random walks, and like what happens with the ever-changing conditions, because scores are changing within seconds and everything. Going to be, I mean, there seems to be an implicit assumption that you know the graph. You don't know the graph in a
no, there's no assumption. This protocol, this algorithm here, we have two things on the plate, right? This one and this other thing that I'm promising to talk about. This thing, the random walks are done simply by like making a network call, so they happen recursively. That costs whatever it costs, but the way to think about it is that gossip sub score updates, they happen only after one broadcast has finished. So definitionally, the 1 unit of work for gossips, so scores cannot be updated more frequently than an actual broadcast happens. So instead of like reasoning about it,
that's not necessarily true. So the broadcast may not reach all nodes by the time you update the scores in some nodes. Also, what's to prevent the Sybil to launch it? But what's to prevent the Sybil to launch a denial of service attack? An army of Sybils requesting random walks and overloading the network with random walks.
Yeah. So actually, this paper doesn't address this, but it's actually very easy to address because you can just put a simple quota of. So for every node, you can just put a simple quota of whatever you expect the number of the average expected number of random walks to be per node, then you can just make a quota. And so like this takes care of denial of service attacks like right away.
Since it's deterministic, it can also be cached.
Yeah,
right?
Yeah. And my big point here is that really walking these diffusion paths is actually much less work than what the gossip sub is actually doing, which is full-on broadcasts. And so you can you can basically make a calculation that if everybody was to perform, I mean, it's a fair question. If everybody was to perform a calculation of their diffusion, so n nodes times square root of n, so that basically does take a while. It takes square root of n broadcasts worth of time. So to your point, this network will be sensitive to changes in scores, at least every square root of n broadcasts, or you might want to space it out even more. So it is a valid like thing to have in mind.
So one problem with the quotas for the random walk sorting, you're saying that the random walks are recursive. So basically that means that a Sybil starting a random walk or an army of Sybil starting a random walk on some node are going to block the other nodes for performing any random walks. So that's why you usually avoid recursive algorithms in distributed systems, exactly for this reason. You try to use iterative algorithms.
Yeah, but again, at every node, so here's the thing, right? Though it's actually even easier here because the answer to a random walk request is let me put it differently. I think this question falls actually entirely in the topic of how do you prevent denial of service attacks, but generically, because nothing prevents any node from just sending bogus, network calls to you. They don't have to be calls for a network, for a random walk. They can just be bogus calls. And whatever you use to stop these, my point is that like a network call for a walk won't propagate further if this question has already been asked, because remember the random walk is pseudo-random. So the request, you're either requesting a different edge or you're requesting multiple times the same edge. You can't request the multiple times same edge because every node can have a cache and be like, this question has already been asked. So you can't flood the network that way. And the other way in which you can flood the network is just to keep asking questions about random walks. Actually, you can't, because every time you ask a question, really, the question is the edge through which the question comes. That's the only input to the question. So once you ask a question along an edge, you are done. You can't ask the question anymore. So denial of service is basically taken care of automatically because of this. That's because of, let me go to the slides. That's because of, 1 second. 1 second, where did it go? It's because of this. Because if I'm any vertex and I get a request for the next node to go down the path, the next edge is a function of the previous edge, which means I'm only gonna bother answering this network call 1 time per edge, and that's it. If I get more requests,
but the scores are changing, so the edges are changing too. So there's a natural limit to how long you can cast, for that might be just a few seconds.
So
I'm not even that.
Yeah, so I'm more sort of in a relative analysis, every time an edge changes, you will be opening up a quota for 1 more network call on this edge. Yes, and so so that's the rule. And so then as a designer, you can pick how frequently relative to useful payload am I going to make changes to these like reputation edges. But I should say that even just like looking, ballparking it, it seems unreasonable. So of course, a gossip subscore can change on every single useful message that gets transmitted, but this change doesn't need to be integrated in the reputation system right away, because really a meaningful change of score happens probably after a few, misbehavior has lasted for a little bit. I mean, if you react to just a single message being dropped, then you are essentially also definitionally cutting off people who just had a network glitch for a moment. So if you believe that you don't want a network glitch, small network glitches like a 30-second network glitch, probably you don't want this to mark a node as bad, which implies that you won't be changing reputations that frequently, like you would be changing the reputation based on the score, like every 1 minute, for instance. But again, this is all, I think these are valid questions because it does depend on questions of speed, right? Because if you're saying that you're expecting a bunch of CBUs to show up and then start attacking the network really fast, and if you're saying, well, I want to react really fast, reacting really fast literally means, well, if you see a dropped message, then you mark them as bad. So if that's what you want, then this would be awkward to use. But then I say, is that really what you want? Because that also means that under normal operation, you're cutting off good guys because they have network glitches. So it's a balance between these two things that I think.
Right, I'm just gonna note that we are at 90 minutes here, which is fantastic and is a good signifier of how engaging this topic is and this talk. If anyone has any last questions that they really want to ask while we're recording, please feel free to. I'll give you about 8 seconds to chime in here.